Hello, I welcome you all. The problem reads the spring has a stiffness over 50 pounds per feet and an unstretched length of 2 feet. As shown, it is confined by the plate and wall using cables so that its length is 1.5 feet. A 4 pounds block is given a speed VA when it is at A and it slides down the incline having a coefficient of kinetic friction 0.2. It strikes the plate and pushes it 0.25 feet before stopping. Determine its speed at A, neglect the mass of the plate and the spring. This problem is coming from the Engineering Mechanics and Dynamics, a 14th edition by R.C. Hibbeler. Let's draw the free body diagram. We do have the weight acting through the center of gravity. We do have the normal force, like so. This is sliding down and there is some friction, kinetic friction. We expect it to be in the opposite direction, like so. Right? Okay. Something like so. Let me write this properly. So have something like that. Alright. We are going to have components of this particular weight. So have one component in that direction. Okay. And we'll have another component in that direction. Okay. Then we do have this angle here. I can use this triangle here. You've seen this one, you can use this for the angle. For me, sometimes I prefer to just calculate the angle. You don't have to do this, you can use that directly. So let's say this is my theta here, and I know that tan theta, okay, is just equal to, because this is the one here, is equal to opposite 3 divided by 4. Therefore, theta, I know that 0.75, tan inverse of that is just a 36.87. This I know it. Let me confirm it. 0.75, tan inverse of 0.75. Yes, 36.87. Okay. So having said that, so there we go. We have that one there, and this incline, like so. Okay, so this angle here we are saying is theta, and if it's theta, this one here is 90 minus theta, therefore this becomes theta also, right? Of course, why not? So this is theta. This is our weight, so this just becomes W sine theta, and this one is W cos theta. This is the normal force, and this is the kinetic friction. Let's add some details to this. So this spring is already displaced by these cables. Okay, so we need to account for that. So we are saying the moment this particular block hits this particular spring, the spring gets displaced by a certain amount, which is, we've been told here, 0.25. Okay, so let's say this is 0.1 and this is 0.2. So our S1 as our initial displacement is equal to the original length and stretched 2 minus the restraint there. So S1 is just equal to 0.5. Then S2 is going to be equal to 0.5 plus 0.5 plus the deformation itself, like so. So S2 is just equal to 0.75. Is that okay? Yes, that's fine. Great. So let's write down the equation. We are going to be using the work and energy. So the initial kinetic energy plus the total work done from point 1 to point 2 is equal to the final kinetic energy. We do have the initial velocity, but we don't know it. We are calling it VA. Let's call it V1 for now. Then the total work done here, we're going to say from S1 to S2, the work done by the spring ds. And then we also have another work done by the friction, which is in the negative direction. We have friction like so, then we have displacement like so. So this gives us negative work, right? So this is just going to be equal to minus Fk times 3 plus 0.25. This is how much the spring has been deformed. Then we also have another piece of work by the weight, and this one is positive. We'll say plus W sine theta, okay, plus times 3 plus 0.25, like so, equal to 0. They are in the same direction like so. W sine theta and the displacement. So here we have positive work. So that is the work that we intend to do. So let's work on the integral first. We said S1 is equal to 0.5 and S2 is equal to 0.75. So integral S1, S2, Fs ds is just going to be equal to integral 0.5, then 0.75, and a minus. This one takes care of the direction, S ds, and this just becomes like so if we integrated this from 0.5 to 0.75. So if we went further, then this just gives us our stiffness is 50, so we have a minus 50 divided by 2. Then we open brackets, then we'll have a 0.75 squared, 0.75 squared minus a 0.5 squared, like so, which just becomes equal to minus 25 by, this one we can work it out, these are just all numbers. So we have 0.75 squared minus 0.5 squared times 50 divided by 2. So this is just going to be equal to minus 7.8125. 0.75 squared minus 0.5 squared, okay, times minus 50 divided by 2, minus 7.8125. And then let's work on the friction. We'll say summation of forces in the y equal to MAY, but we know that our AY is just equal to 0. Therefore, we are going to have N minus W cos theta equal to 0. Therefore, our N is just equal to W cos theta. And we know that Fk is nothing but equal to mu k N, which is just equal to 0.2 times W. So this just becomes mu k W cos theta. Okay, right, and this is just equal to 0.2 by the weight of the block. What's the weight of the block? It's a 4 pounds. Then cos 36.87. Therefore, Fk is just going to be equal to, that's 0.2 by 4 by cos 36.87. So this we get a 0.63999. Therefore, this just becomes 64, like so. Is that so? 0.2 by 4. 0.2 by 4 cos 36.87. 0.64. Right. Okay. Therefore, Fk times 3 plus 0.25. This is just equal to 0.64 by 3 plus 0.25. This is the work. And this just gives us 0.64 times 3 plus 0.25. And this is just going to be equal to a 2.08. Okay. All right. Then we work on the other one, which is W sine theta times 3 plus 0.25. This is just going to be equal to 4 sine 36.87 times 3.25. This is equal to, that's 4 sine 36.87 times 3.25. So this gives us a 7.80. Okay, so 4 sine 36.87 and times 3.25, 7.80. Alright, so there we go. So we have calculated these. Let's now place them in our equation. So writing everything in our equation, we'll have half. The mass is just 432.2 times V1 squared. Okay, then we do have minus 7.8125. Okay, right, then we have the work due to friction minus 2.08, then plus 7.80 equal to 0. So making V1 subject to a formula, don't forget to square that. Don't forget that. So we do have a minus 7.8125. then minus 2.08, then plus 7.80. Okay, then divided by 0.5 by 4 divided by 32.2, like so. Okay, all right, and then square root of answer, we find a 5.80. Let's repeat this once more. Minus 7.8125 minus 2.08 plus 7.80. Okay, then divided by 0.5 by 4 divided by 32.2, and square root of that 5.80. Our V1 is just equal to VA, which is equal to 5.80 feet per second. So that is the speed at A. Alright, so I guess we have found VA, which is the speed at A, neglected the mass of the plate and the spring. I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screencast.